Let us find the location and nature of the critical points of the following function. It's a multivariable function, a function of x. The variables x and y as well. It says f of xy is x squared minus y squared. Now, just to review what we're supposed to do, we're going to find the derivative with respect to x and the derivative with respect to y. We're also going to find the second derivatives. Derivative of x, second derivative with respect to x, then the second derivative with respect to y. fxx, fyy, and then fxy. And we could also find fyx as well. We expect it to be equal to fxy. Alright, then after we find the first derivative with respect to x and the first derivative with respect to y, we equate each to 0. Right? Then we solve and find the locations of the critical points. Then we're going to evaluate D, where D is fxx of the 2 points, the coordinates of the location, times fyy, we substitute the coordinates of the location, minus fxy, where we substitute the coordinates of the location, and that will be squared. And we do the second derivative test. If d is greater than 0 and x less than 0, then we have a maximum point. If d is greater than 0 and xx less than 0, or greater than 0, both of them greater than 0, then we have a minimum point. And if d is less than 0, then we have a saddle point. So let's find fx, fy, fxx, fyy, and fxy. So here now, fx, when we, not f of x, fx. Now remember, this will be same as del f by del x, which we call fx. Alright? Now, we differentiate this with respect to x. X is considered a variable, so we have 2x here. Y we treat as a constant, so when you differentiate a constant with respect to x, we get 0. Here, let's find del f by del y, which we also call fy. We're going to get negative 2y. The same reason as before. Y is our variable, and we treat x as a constant. Now, let's differentiate and find del square f differentiated with respect to, well, del f by del x. We differentiate that with respect to x again, so we call it del x squared. Remember, this is what we differentiate with respect to x, so we call it del x squared. It is what is referred to as fxx. Alright? So, when we differentiate this with respect to x, what do we get? Well, we're going to get 2. And then here, del square f by del y squared. Same thing as del yy, or fyy. What do we get when we differentiate this with respect to y? we get negative 2. Alright? Now, suppose we find del squared f with respect to del x, del y. Right? Now, this is the same thing as f yx. This is saying you differentiate with respect to y and then with x. Same thing this is saying, it's just that you move from right to left here and you move from left to right with this notation, right? So, here, we look at what we differentiated with respect to y, then do it with respect to x. This was the derivative with respect to y. If we differentiate this with respect to x, we get 0. There's no x there, right? And then, if we find del square f by del y del x, same thing as saying we find f x y, right? We look at what we differentiated with respect to x and then we differentiate it with respect to y. Remember, I don't really need to find both fxy and fyx because they, we expect, will be equal, but we still do it here anyway. Right? We're not in exam, so we have enough time to play around with this thing. So, look at what we differentiated with respect to x and then we differentiated it with respect to y. Alright, the derivative with respect to x was this. When you differentiate that with respect to y, we get 0. Alright, good. But anyway, let's find the location of the stationary points. It may be one or more. In this case, I expect that there will be one stationary point. But let's look at what happened. We had fx and we had fy. Let's equate each to 0. Let fx equal 0, let fy equal 0. That means 2x equals 0 and negative 2y equals 0. Alright? Remember, del f and del y would be fx and fy would be this and this, right? So, they were 2x and negative 2y. So let's 2x equals 0, negative 2y equals 0. When 2x equals 0, x would be 0. When negative 2y equals 0, then y would be 0. Alright. So, here now, we find out that there is one critical point. It is located here. X equals 0, y equals 0. Alright? Now, thing is this now. We want to run the d-test, the nature of the critical point. Let's look back at the d-test. D is fxx. Now remember, before we do that, when we solve the system of equation, we found fx equals equated to 0, fy equated to 0, and we put them together and let AB represent a solution. Now, our AB is equal to 0, 0. That's our AB, right? Now, here, we want to find D. What is that equal to? D is fxx AB. So let's write that down. It's fxx AB. Right? So, when we found fxx, we got the function. We're going to put the value of a and b in it to find out what it is. Fxx AB. Then we multiply that by fyy AB. So that's fyy AB. The point that they put there, it means multiply. Just that they, instead of the multiplication side, they put the point. Right? Minus f of xy, no, fxy AB squared. So what we have is fxy AB. And that's squared. So fxx AB. fxx was 0. Right? So what we have is D equal 0 times fyy. Fxx. Where was fx? Oh, fxx was 2, not 0. I was looking at the wrong thing a while ago. 2 times, and then fyy was what? Negative 2. So we have this and this multiplied, minus now fxy AB squared. Fxy was 0, same as fy is 0, and 0 equal, what does this give us? Negative 4. So let's look and see what our formula sheet here for the D test says. Okay, D is negative 4. We found a while ago. And this says if f has neither a maximum nor a minimum at AB, if D is less than 4, the function has a saddle point. Alright. So in this case, it is a saddle point at 0, 0. So what we have is a saddle point at 0, 0. Right? The thing is, if, first of all, if we have our x, if we had our x, our y-axis, and our z-axis, right? We have x, y, and z-axis. If we had a maximum point, we would have the x going up and then down, and the y in the direction of the y would be somewhat like this, right? That would have been a maximum point, right? So, like a surface that we would have, looking at that. If it was a minimum point, then the x would go down and then up in the direction of the x. The y would also go down and then up. So, what we would have, also a surface, what this would be a sink, like you put a stone on a handkerchief and it sinks down. Alright? Like a basket. But it's a saddle point that we got. Right? So in that case, it could be that the x goes up and down. The x, in the direction of the x-axis would go up and down. But the y also go up and down, but it would look more like that. Alright? And then it would look more like a horse's saddle. Let me see if I could draw what that would look like. You have some drawings on the internet what it would look like, alright? Or if you look for the image of a saddle, you might see something like this. Right? How do I draw this saddle now? How do I draw a horse's saddle? It might be something like this. Right? You have this part you put over the horse's back, but the part that you sit on is down like this. So you have the x value going up and down like this, but the y value also go up and down. But the x might have a maximum point and the y a minimum point where they meet. So there is no true maximum or minimum point. So it's like a saddle. But anyway, that will be for this question for now.